Okay, camera's on, guys. So today my question for you is, what is your favorite book? Luis Acevedo. Luis? Katrina Atkinson. Luis, what's your favorite book?
My favorite book is actually Renatos where he traveled and his motorcycle in Spanish.
I was recording and I paused it for when you guys were telling me your favorite books. I thought I'd try to keep that out of the recording, but thank you. I appreciate that. I had totally forgot to press record again. So probably the easiest way to let's look at the formula for covariance first, and then I'll show you like a very simple example that will hopefully clarify it. So the covariance between X and Y is really kind of simple. So you're going to calculate the distance between X and its mean. Okay, why is that? Sorry. My new stylus is, I'm just getting used to. So this is basically to calculate the distance between each observation X and its mean, and calculate the distance between each Y observation and its mean. And then multiply those together for every observation and add them up. And then like we did before when we had variances, we're dividing by 1 over n minus 1. Okay, 1 less than the sample size. So just let me write this here. No bother. Each data point and sorry, this stylus is not very good. And my mother-in-law is sending my stylus back, so hopefully I'll have it in a couple of days. And the average. Okay, so we're going to multiply those together, add them up, and then divide by n minus 1. So let's do a really simple example. I'm going to just clear this so that we don't have too much clutter on the page. Okay. So say we have, I'm going to keep doing this because it's really simple, but a data set of 2 observations, okay? So we're going to have a data point here. We're going to have a data point. We're going to have a data point here, okay? And just to make it simple, we'll have this will be y2 and y0. And then the x will be similar, will be 0 and 2. We're just trying to make the math really simple. So let's calculate the covariance together. But first, just with your eyes, you can see that when there are larger values of x, y is a larger value as well. So first, we're going to calculate the average. The average x is going to be 2 plus 0 divided by 2, which is 1. And the average y is going to be the same. 2 plus 0 divided by 2 is 1. So what we're going to do is just go through this, but luckily for us, because we only have 2 data points, we'll only be summing 2 of these products. So the first will be 2 minus 1 times 2 minus 1. Remember, that's because this is 2, 2, and this is 0, 0. Sorry, 0, 0, plus, let's see here, 0 minus 1 times 0 minus 1. And then that will all be divided by 1 over 2 minus 1. So here we have 1 times 1, which is just 1, plus 0 minus 1 is negative 1, and 0 minus 1 is negative 1. So we actually have 1 plus 1, all times 1 over 1. So it's going to be, we're going to get 2. So the main thing that we learn here is that there's a positive, because this number 2 is positive, there's a positive covariance between X and Y. And the really nice intuition is just when values of X are higher than average, values of Y are higher than average. When values of X are lower than average, values of Y are lower than average. So it tends to be, though, that we don't have data sets of 2. We have data sets of, hundreds or thousands and sometimes millions. So instead of being 2 little points like this, we usually have kind of a data cloud like this, lots of points. Okay. And so this one is, if you added up, if you did this formula for all of these points, you would still get a positive number, because when a point is higher than its average in X, it tends to be higher than its average in Y. So let me do the opposite example really quick. So the opposite example is, if, say, we have 2 points, but they go the other direction. So when X is high, Y is low. Okay. So this is going to give us a negative value because the product of these are going to tend to be negative. And I'll show you that really quick. So we're going to have 1 divided by 2 minus 1, all times, remember the average of X is 1 and the average of Y is 1. So X is, sorry, so this is 2, 0, 0, 2. Okay, so it's going to be 2 minus 1 times 0 minus 1 plus 0 minus 1 times 2 minus 1. So this will be 1 times negative 1 plus negative 1 times 1. So here we're going to have, well, this will be negative 1 plus negative 1, so negative 2 divided by 1. So what does that mean? It just means that when we have large values of X, we tend to have small values of Y. There's a negative covariance, okay? Okay. So here's a little example we can do together. A bigger example, I guess. So we've got X's and Y's. got row of X's and a row of Y's. And I'm going to do a little favor. And I'm just going to calculate the average X and the average Y for us. And then we can just use our formula that we've been using in the last slide. And we're going to try to calculate the covariance between X and Y in this example. So what are we doing? Let me just try to push this up a tab. Is we're going to go, each of these will be one data point. Each of these products will be one data point, one observation. So we're going to take, for instance, we're going to take 2 and subtract the average of X times 6 minus the average of Y. So that's what we get here. 2 minus the average of X, which is 4, times 6 minus the average of Y, which is 8. And we're going to do that for each of these different rows. So that's where we get 3 minus 4 times 8 minus 8, and then 5 minus 4 times 7 minus 8, 6 minus 4, this last row here, 6, the X value minus the average X times the Y value minus the average Y. And then 2 minus 4 is -2, 6 minus 8 is -2 as well. 3 minus 4 is -1, 8 minus 8 is 0, 5 minus 4 is 1, 7 minus 8 is -1, 6 minus 4 is 2, and 11 minus 8 is 3. So what we're going to get is 1 over 3 because of this, because we're multiplying the whole thing by 1 over the sample size minus 1, and the sample size is 4. So it's 1 over 3 times 4 plus 0 minus 1 plus 6, and that's going to give us 3. So the covariance is 3. Let's do a little plot of this data really quick. That's sometimes much simpler to just see the data. So our highest value will be 6. Our smallest value will be 2. Let me see here. 2, 3, 5, 5, 4, 3. Here, the largest value is 11. Smallest value is 6. 6, 7, 8, 9, 10. So that's 4. So I'm going to try to make these as even as possible. Not great, but not bad. 10, 9, 8, 7. Okay. So I'm going to plot these. So 2, 6 is 2, 6 right here. Okay. 3, 8, the second row is going to be 3, 8 right there. 5, 7, go up from 5x to 7. And 6, 11. 6, go up all the way to 11. So if I give you these points, that's pretty bad. You would tend to see that when there are high values of X, they correspond to high values of Y in the data. So that makes sense that we got a positive value for the covariance between X and Y. Because if you kind of were to draw a line through these points, you would say, yeah, that's a positive, mostly positive association. Okay, let me pause and take questions here. Can you go back up? Yes. Let me see what time it is. Okay, go back up to the previous slide. Awesome. And just so you know, all of the slides are uploaded to Canvas. So you have everything that I'm using in class. Okay. So questions here. Let me just call on a couple people. Warren, Yesenia, Stephanie, Saul, Manuel, Ned. Any questions here? Everything good?
Just to clarify, you got your 1/3 from plugging in 4 on the end?
Yep. So we're just exactly. We just said how large is the data set? Data set is 4. So we get 1/3 by saying 1/4 minus 1 is 1/3.
All right, thank you.
Yeah, my pleasure. Thank you for asking that. Okay, how do we find X bar and Y bar? Great question. Okay. Sorry, let me declutter this a little bit. Okay, so what's X bar? X bar, oops. X bar is the mean of X. What's the nice of X? No one knows. No, I'm just kidding. Sorry. The mean of X. So all we're going to do is add up 2 plus 3 plus 5 plus 6 and divide it by the number of observations, 4. So what's that? That's 5 plus 5 is 10 plus 16 is plus 6 is 16. So we're going to get that 16 divided by 4. So that's 4. So X, whenever we have an X bar or a Y bar, X bar equals the mean of X. Y bar equal to the mean of Y. Yeah, perfect. Thanks for pointing that out. That would have been very easy to miss. So thank you. Other questions? Okay. Let's do one more example. So here, we have 4 data points, and I'm going to calculate the mean of the X and the Y for you, just to make your life a little simpler. And we're going to use our formula of covariance like this. And so all we're going to do is first we're going to say how far is the first X from its mean. That's 13 minus 7 times how far is the first Y from its mean, 4 minus 8. We're going to multiply those together. And then we're going to go to the next observation in the data. 8, how far is 8 from its mean? How far is 9 from its mean? And we're going to go to the third observation. How far is 5 from its mean? Times how far is 9 from its mean? And then finally, the last observation, how far is 2 from its mean? 2 minus 7 times how far is the Y from its mean? 10 minus 8. So we're going to multiply all those together. So we're going to have 6 minus 4 times 1 times 1 times negative 2 times 1 times negative 5 times 2. You're going to be able to add all those up. 24 is 6 times negative 4. 1 times 1 is 1. Negative 2 times 2 is minus 2. And negative 5 times 2 is negative 10. Got a very helpful question last time. Where does this 1/3 come from? It comes from the sample size. So all we're doing is saying 1 over the sample size 4 minus 1. That's going to be equal to 1/3. Adding 24, 1, -2, and -10, we get a new number. Oopsie. -35 divided by 3. And that's to divide by, by a number that isn't a factor. That number is always kind of goofy. So you get -11.66666, or we round up to 67. Okay, so let's just plot this data really quick to see what that's saying. So we're gonna have the x's down here and the y's right there. And let's see what our values are. For x, we've got between 2 and 13. So this will be something like 7. This will be something like 4. I'm not going to do every number because I just don't think do something like 10. Okay. And then y's are between 4 and 10. 4. This will be something like 7. Okay. So we're going to plot the first point is 13, 4. The second point is 8, 9, 8, 9. The third point is 5, 9, 5, 9. And the final point is 2, 10, 2, 10. Okay, so what you tend to see is that when x is large, y is small, and when x is small, y is large. Okay, so that's what we're learning when we see that we have a covariance that's negative. It just means, the other way to say it is that there, if you drew a line through it, you get a negative slope. Okay. Questions there? No? Awesome. Devin, thanks for having your camera on. I appreciate it. Okay. Okay, so that's covariance. Correlation is very similar to covariance, but it's slightly different. So correlation is a measure of how much variables change together. So we normalize it, which means we divide it by something that makes it so that it's very easy to compare across different data sets. So the ranges of a correlation vary between -1, which means a perfect negative relationship, perfect negative correlation, and +1, perfect positive correlation. So typically, so this is the formula really quick. The formula is nice because it's made of things we already know how to do. So the correlation is the covariance between x and y. Correlation between x and y is the covariance between x and y, which we just learned how to calculate, divided by the standard deviation of x times the standard deviation of y. That's all it is. That when we say normalize, by dividing by the spread of both variables normalizes uh, the correlation. So that's why we're always able to say, oh, this is -1 is a perfect correlation in any data set, a perfect negative correlation in any data set, because we're dividing by how spread out X is and how spread out Y is. I'm going to delete that because it's so messy. Okay. Okay. So I just wanted to give you a couple examples of this. Okay, so the first thing I wanted to show you is just, this is kind of cool. So I guess I should just redraw it so that it's clear. So first, say that we had 2 data sets and one there's a positive correlation like this. So if we drew a line, we'd be able to hit each of the points with the line. So sorry, you can't see those points very well, but this would have a correlation of 1. Okay. Say we had another data set in X and Y where the points were similar, except the slope was greater, but you were still able to draw a line through them, all the points. This would also have a correlation of 1. So the correlation isn't telling us how steep the line is, it's just telling us how perfect the fit of the line is through the points. So by contrast, if we had a data set like this, this is pretty common. So when we draw a line through these, we're not able to hit every point. There's some space between the points and the line. This is a correlation. This is probably actually still quite a strong correlation. So this might be a correlation of something like 0.8. So instead of 1, it's a correlation of 0.8. It reflects the fact that it's that the line isn't exactly on top of all the points. But many of our data sets, almost all of them, are much weaker than a correlation of 0.8. So most of them will look something like this. So that would actually still probably have a positive correlation, but you could imagine that it's not very strong. So this might be something like a correlation of 0.2 or something like that. So let me show you a couple other examples of this. So if you had a data set with where the data points are going down, that's going to be a negative correlation. This might be a negative correlation of -0.8. And then you could have, and it's actually quite common, you can have a correlation that's basically 0. So say you've got all this variation in X and Y, and the line doesn't really point in any direction and it doesn't fit the data very well. This will be a correlation of about 0. Okay. Questions here? Okay. So we can do, let's do a correlation calculation together. Here's our data set again. I don't know if this is the same as one of our other data sets, but We've got 4 observations, 2, 6, 3, 8, 5, 7, 6, 6, 11. And instead of calculating the covariance, the standard deviation of X and the standard deviation of Y, I'm just going to give it to us so that we can just focus on calculating the correlation rather than calculating all these other things. So remember the formula for correlation. Correlation between X and Y is equal to the covariance of X and Y divided by the standard deviation of X times the standard deviation of Y. So we're just going to plug in our numbers here. We've got 3 is the covariance between X and Y, divided by the standard deviation of X, 1.8 blah, 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 times 2.16 blah, blah, blah. And that's going to give us that the correlation is 0.761. Okay, so let's plot this really quick and just see what the data look like. What does a correlation of 0.76 look like? That's pretty high. So we got the biggest X is 6, the smallest is 2, and then we got 3, 4, 5, so 4, 3, 5, and then Y we've got 11, 6, 7, 8, 9, 10, 7, 8. Okay, so we've got 2, 6 right here, 5, 7, it's right here. I'm sorry, I skipped one. 3, 8, it's right here. And 6, 11 is right here. Sorry, that was confusing. I did this one, then this one, then this one, then this one. I'm so sorry, that must have been confusing. But just plotting the points, and then you can see there's a nice positive relationship between them, but the points are actually not all very close to the line that fits them. So that's why it's not a correlation of 1, it's a correlation of 0.76 or something like that. Okay, so let's see what we got next. Okay. So the nice thing about your eye is it's actually very tuned to seeing slope. So you'll say, this is clearly a positive slope, this is clearly a negative slope. Correlation doesn't measure the slope. You can have a perfect correlation of 1, even if the slope is quite shallow. That's just an important thing. These 2 points, these 2 series right here will probably both have a correlation very close to 1, even though 1 is very steep and 1 is very shallow. Okay, so that's it for correlation and covariance, and we'll work on that in the homework today. So these are just some properties of summation that are going to be really helpful for understanding means and variances and standard deviations and how they're affected. Often when we add them together or when we multiply them by something else. So I'm just going to go through these with you and show, and we'll kind of discuss. I'll show you why each is true. So the first is that if we were to take a constant c and we were to sum it n times, it's just the same as if we multiplied c by n. I'll show you that in the next slide. I think or maybe in 2 slides. So that's property 1. Property 2 is that if we summed x, it's actually the same as if we multiply the mean of x times how many x's there are. I'll show you that too. So if you want to know how, for instance, how much income is earned in the whole country, and I told you what the average income in the country was and how many people there were, you could just multiply, how many people there are, 330 million people, times the average income, 40K or something like that. 40K or something like that. I mean, you'd be able to find the total income with the average and the number of people in the sample or in the population. The third is that if you multiply a variable by C, so say we had, for instance, your height in feet, and we wanted to rather know your height in inches. So we multiplied, in the data set, we multiplied your height in feet by 12. So it would be in inches instead. Instead of multiplying 12 by each of the numbers and then summing it up, you could just sum all of the height up and multiply it by 12 afterward. Those are the same. And I'll show you that in the next couple slides. The fourth property is that if you have a sum if you're adding two things in a summation, you can split that into two different summations. So that's just sometimes useful because it can clarify or simplify something. So I'm not going to take questions just yet because I'll show you each of these in greater detail in a moment. Okay, so the first one is that is I'm going to just show you why when you add C n times, you just get n times C. That's the same as multiplying n, the number of observations in your sample, by C. So if we were to sum C n times, it would just be C plus C plus C plus C n times, which is just the same as multiplying C by n. Any questions on that one? Okay. So this is a really cool one. I like this one a lot. So if you were to add up all the x's, it's the same as multiplying the average x times the number of observations. So one way to see this is like a very routine math trick, is that, watch this. So n times 1 over n is equal to 1 because the n's just cancel out. So sometimes we do this, we multiply by 1 because it doesn't change anything, but sometimes it clarifies something that's going on. So we're going to multiply this whole thing by 1 in the form of n times 1 over n. So that's how you can see that these, the left and the right side, are equal. And then we're going to notice this, that 1 over n times the sum of the x's is equal to the average of the x's. So the n will just carry down, and this chunk right here is equal to the average of x's. Question here? Okay, cool. Please break in if you have questions, or if I'm going too fast or saying something wrong, please break in and let me know. Okay, so this is a cool one too. So instead of multiplying a constant by every part of the data, we could just do the summation first and then multiply that sum by the constant if we were interested. So that's the example where say we had in the data your height in feet and we wanted it in inches, or sometimes it's different. Sometimes we have your age in months, but we want it in years. So instead of multiplying by 12, we'd be dividing by 12. If we had it in months and we wanted it instead in years, we'd be dividing the number of months old you are by 12 to get the number of years old you are. So if we were to do this, if we were summing the c times every x, we would just have c plus x1, I'm sorry, c times x1 plus c times x2, etc., plus c times xn. And we know that when there's a common factor added in all of these different things, we can pull it out of the parentheses. We can factorize. So we're going to have, that's equivalent to c times x1 plus x2 plus x3. And of course, x1 plus x2 plus x3, etc., is the same as a sum of xi. So that's how we know that, that this property is true. So one thing I think that's true is if you go through these and do them by your hand, it makes you smarter. These are really good mind jungle gyms or mind training, just like to see how each of these is equal and how they show the proof is a really great training in thought and attention. Okay. So the last one that we'll do today is that we can break a summation like this into two baby summations like these. This one's probably, I think it's the simplest to see, which is this. All this means in practice is that we're summing x1 plus x2, I'm sorry, x1 plus y1, and then x2 plus y2, et cetera, all the way through the data set. We're just going to take all of the x's and put them together. So we're going to go we're going to put x1 and x2 and xn all in the same parentheses, and we're going to take y1, y2, and all the other y's and put them in the same parentheses. And then it's pretty simple to see that this is just the sum of x1, the sum of xi, and this is just the sum of yi. Okay. So questions on any of that? Questions from those or anything else that we covered? Okay, awesome. Let's go and work on some homework. Let's see here. We're going to go back to assignment 1. Okay, so this is what we were working on yesterday. Let me just clear the slate, clean the slate. Okay. So it's asking us, what is the covariance of wage and experience? Is this consistent with your figure plot, your plot in before? Okay, cool. I'm excited about this. Okay, so what was our formula for covariance? The covariance, I'm gonna put it up here. Covariance, oh my goodness. Covariance between x and y is going to be 1 over n minus 1 times the sum of x I minus x bar times, sorry, yi minus y bar. Okay, so what's our x bar? We had this from yesterday. Does anyone have that handy? Maybe I have it. Okay, I have that the average wage was 13.3. Is that what you guys had yesterday?
Yes.
Something like that. So that we're going to have Y be our wage. And then my average X was something like 4.5. You get something like 4.5.
Yes.
4.5, awesome. So this is a little bit harder than the ones we did before, but not much harder. It's just that we have 6 data points instead of 4 or instead of 2. So, excuse me. Okay. So we're going to do 1 over 6 minus 1. So that's going to be 5 times 8 minus 13.3 times 1 minus 4.5 plus 20 minus 13.3 times 10 minus 4.5 plus 10 minus 13.3 times 2 minus 4.5 plus 12 minus 13.3 times 4 minus 4.5 plus 16 minus 13.3 times 4 minus 4.5 plus 6, no, sorry, I already did 16, 14. 14 minus 13.3 times 6 minus 4.5. Okay, it's a huge mess. Let me see if I can do this on the calculator. But yeah, setting it up is kind of the main, what's it called? Oof. Okay. Okay. Has anyone gotten an answer on that one? I'm gonna just hang out for a couple minutes until a couple people can get a result for that. Oh, you did. Devin, what'd you get?
Oh, I'm plugging it in right now.
Oh, I'm sorry. Keep going. Keep going. That's great. Luis, Ibrahim, Katrina, Kimberly, Leanna, Luis, Noah. I'll call on a couple of you guys.
12.8.
12.8. Yep, that's what I got too. Good. Okay. So did anyone get stuck? I'm sure I would have gotten stuck. Did anyone get stuck? Um, okay, so that is great. No one got stuck. If you got stuck, please feel free to break in and let me know, and we can talk about anything that was confusing. Okay, so then the second part of this question asks, is this consistent with the line you drew in part C? So what do you guys think? Is 12.8, is that consistent with the line that we drew? So I would say yes, it's perfect. Thanks you guys for doing that. Yeah, yes, it's consistent. So when we did the plot, we had kind of the dots going upward. And so what we have here is a positive covariance. So it makes sense that we saw the dots going upward because for large values of X, we saw large values of Y. And that's what the covariance says, and that's what the plot said at the same time. Okay, so we've got this covariance of 12.8. Covariance was equal to 12.8. So the last question of this homework asks what's the correlation between wages and experience? So this is, we don't need to do much more math. Remember that the formula here is that the correlation is equal to the covariance divided by the standard deviation of X times the standard deviation of Y. Okay, so we have the covariance. What was the covariance again?
12.8.
12.8.
Perfect, 12.8. And what was the standard deviation of X?
Uh, 4.31.
Perfect, 4.3, 4.31 or 4.32 or something, times what was the standard deviation of Y?
3.2.
3.2. Okay, does anyone have that handy? Let's see.
.93.
Yeah, I got 0.92, but it all just depends on how many decimal places you include, I think. So 0.92, 0.93, all that's good. So that's a pretty strong correlation. It means that there's not a lot of distance between the data points and the line that you're able to fit on that data. So that is the completion of this homework. So good job. I'm going to post that to be due on Thursday at midnight, or Thursday at 11:59 or whatever it is. And it's already done, and you can review this recording. So I think you have everything that you need. Are there any questions on the homework? Any questions about this calculation or the calculations before it? No? Okay. So, just one sec.
I have a question about
Yeah.
the homework. So since this one kind of involved like math, when we submit it, do you want us to like take a picture of like our work and submit it as like a PDF?
Yeah, no, it'd be great to either scan or take a picture. That'd be great. Oh, please submit it on Canvas and not into my inbox. My inbox just doesn't have, it's hard to organize and find some of the homework sometimes when I get a lot through my inbox. And it's very easy to grade on Canvas because it just has all of them right next to where I enter the grade. But yeah, ideally you would show your work just in part. It's really good practice. So I want to see that you're you know how to set it up and all of that. So that I just know that that's working.
Thank you.
So let's call it quits for today, and we will meet. I'll see you again tomorrow. The homework is due on Thursday at the end of the day, 11:59. Am I missing anything? We just finished quicker than I thought we would today. So yeah, we'll conclude there. You're welcome to go, and I will hang back and take questions.
Where are you going to post today's video? On YouTube?
I'm going to post it on YouTube and send you the link.
Okay, thanks.
Okay, guys, thank you. Thanks for being here.